So, in the previous class, we defined what was a smooth manifold, and I told you that one can define tangent spaces to every point of a smooth manifold. So, let's just quickly tell you how you can do that. So, the construction is very similar to what we have seen for Rn. So definition, so you take, let M be a smooth manifold, then a curve through P in M is a smooth map from a open interval minus epsilon epsilon to M such that gamma not equal to P. Okay, and then what is the tangent? Tangent to gamma at P is gamma prime 0, which is gamma 1 prime 0, gamma 2 prime 0, gamma n prime 0. So this is a manifold of dimension n. Okay, that's what we are assuming. Okay, so that's what is the definition of a tangent space. And then we all know that when you defined, so that because every point in Mn is diffeomorphic, or maybe you can have a local chart around Rn. You can talk about all these things there. Okay, so that gives you. If you collect the property of the, so if you collect the, recall, if this is open, then you take any smooth map sigma to Rn smooth, a directional derivative was given by dvfx limit t tends to 0 fx plus dv minus this by t. Okay, so this derivative exists, and we also have seen that this was kind of vi del f del xi x, where vi is just the component, so v is v1 vn. Okay, so this is what was directional derivative. Now at each so all these we have seen earlier. Okay, so now at each v in Rn, you can associate this operator, which is given by vi del xi at x. Okay, so essentially dxv f, you take a smooth function. Okay, so okay, define this. So this is a operator or on C infinity ux. So ux a neighborhood of x, and this acts as dxv f equal to summation I del f del xi, you evaluate it at x. Okay, so this is the kind of operator that one can define, and then you can observe that this set dxb v in Rn, yeah, has a vector space. So you are fixing x here. You remember, you fix x, and then for each v in Rn you are defining this operator at x. So has a vector space structure over R. Okay, so you have this operator has a, so for each v in Rn you can define that, and it has a vector space structure over R, and the map v goes to dxb is a vector space isomorphism. So what does it mean? So what we are doing here, let me recall. So you take any open subset of Rn, then on the open subset of Rn we identify Tp omega with Rn itself. This we have, and then we are defining we are recalling directional derivative, fix x, and define this directional derivative operator. So this operator, you collect all such directional derivative operator, that's a vector space over R, and it is a vector space isomorphism with Rn. So that means the tangent space at this open set, you can also think of it as this directional derivative operator. Okay, and the operator dxp has the following properties. That is, you take AB in R, then dxb AF plus BG is A dxbF plus B dxbG. So it is linear on real variable, on linear with respect to real numbers. And the second property is a characterization property for such operator. So this such any function that satisfy this sort of property are called derivations. Okay, so a map phi c infinity to R is called a derivation at P if it is real linear and satisfies for fg in c infinity omega. Phi fg is phi f gp plus fp phi. So the directional derivative operators are are derivations on a neighborhood of x. Now it also follows that you take any derivation at p, so one can prove proposition if delta is a derivation at p, then there exists a unique v in Rn such that delta equal to dpv. Okay, and this is defined by, so in particular for some curve gamma through p, some smooth curve gamma through p with gamma prime 0 equal to v, delta f is the same tangent vector that we have seen earlier. So d dt, f compose gamma t at t equal to 0. So just take the tangent vector, take the image of the tangent vector. You remember how we defined that operator df when you have a smooth map between two open subsets. So this definition is essentially the same. Okay, so essentially that means that you have omega in Rn, so Tp omega is, you have a linear isomorphism to dxp, the directional derivative operator, okay, on Rn. So this we did not observe earlier, but now we see that every point in the tangent space on an open subset can be thought of as a directional derivative operator. Now for a smooth manifold, you simply retain this definition. So let Mn be a smooth manifold, a tangent vector v in a tangent vector v at a point p in M is a derivation, is a mapping v c infinity M to R such that v is real linear and v is a derivation. Okay, so this means VAF plus VG equal to AVF plus VG, where AB R, FG C infinity M, and this means VFG equal to VF FP plus VFGP plus FP VG. Okay, and each point P, you take the set of all tangent vectors that is denoted by TPM. Okay, so TPM, the set of all tangent vectors at P. At P in M or Mn. I mean, I'm not writing N, I just write M. Okay, but you sort of keep it in mind that the dimension of M is assumed to be N. So now this tangent vector, they like in the real line we have seen that the partial derivative operators, they generate the directional derivatives. Okay, so now here also you can do that. Just generalize the real calculus setup. So let x1 xn be a coordinate system in M at P for F in C infinity M. Define del f del x I define del f del xi at P to be del f compose phi inverse by del ui at phi p, where u1 un is the usual coordinate system on Rn. Okay, so this is the thing, and you can easily see del xi p C infinity to M to R is a tangent vector of M at P. Okay, so now the point is, I will not again prove it. So this del xi at P form a basis for TPM. That is, for V in TPM, V is simply, so remember we have identified it with derivation. So this gives you the coefficient del xi p. So the dimension of the tangent space is same as the dimension of the manifold. Okay, so now you remember we have defined differential map. So now I just define what I want to differential maps. We have defined it earlier for two open subsets of Rn. But now you start with a tangent vector. Let phi M to N be a smooth map. Then the map, so it's a kind of lemma. Then the map V phi C infinity N to R given by V phi F equal to V F compose phi belongs to T phi Pn. Now proof, check derivation property, and that will give you this proof. Now definition, let phi M to N be a smooth manifold for each P in M. The function, okay, following my earlier notation, d phi p Tpm to Tpn is defined by d phi p of v equal to v phi, where v phi is the above, and this is called the differential map at P. Okay, so that is the differential map is given by d phi p v applied to f is v f compose phi for all v in Tpm and f in C infinity n. So differential maps are linear. So you are approximating a smooth map by a differential map, and then you have all a chain rule, inverse function theorem, everything carries over. Okay. So also it is true that, it is also true that another note that let M, you can prove from all this that you take a smooth manifold and take P in M, then every tangent vector is the tangent vector 2 sum smooth curve in M. Okay, so you can always take any smooth, any coordinate chart. You can always define a curve that will uh, that will that will that will give you that tangent vectors. Okay. So now you know what is the tangent vector, what is the kind of map between two tangent vector. One can define what is a vector field on M. It is just a assignment P to it's just an assignment that every point at P, every point P. So just like you have M, at every point you just assign a tangent vector. That's it. So P in M, you defined a tangent vector xp. Okay. So yes. So that's what is the vector field. Okay. And vector field is smooth if the assignment is smooth. Okay. So for any vector field x with respect to a local coordinate system, local chart u phi, where phi is x1 xn, the vector field will be given by just you evaluate x at xi, just the tangent vector, and then you take the just because del xi span the tangent vector, so this will give you the expression for a vector field with respect to the coordinate system phi, and these vectors, these are coordinate vector field, coordinate vector fields. Now the Lie bracket. So so by this u chi of m, you denote the vector fields. Okay, so by chi of m, the set of all smooth vector fields, and as soon as you have chi of m, you can define what we have seen earlier, the Lie bracket between two vector fields. So essentially the Lie bracket that we have seen, which characterize the Lie algebras that comes from the Lie bracket. That comes from the vector field. So essentially the vector fields give you the concept of a Lie bracket on a smooth manifold. So the Lie bracket is not very specific to Lie algebras only. One can define it on any smooth manifold. However, when you have a Lie group, that gives you one extra structure on the tangent space, which is the algebra structure. And the fundamental theorem of Lie groups essentially relate those algebras with the group itself, and that's why the Lie algebras are kind of special for Lie groups. But even otherwise, one can always define all these things that we have done more generally for any smooth manifold. And as we have already mentioned, that for a Lie group, there is this left and right invariant operators coming from the group multiplication, and if you take the set of all left invariant vector fields, then that identifies with the Lie algebra. Okay, so I think I hope I have been able to give you a brief overview of how smooth manifolds works. Now here is a reference for smooth manifold that I would like to give you, and I will stop the lecture here. So reference for smooth manifold is this book by, you can look at this book by John M. Lie, An Introduction to Smooth Manifolds, for a comprehensive introduction. There is also a book by S. Kumaresan that also you can have a look. And the name of the book I would like to write down. So this is called A Course in Differential Geometry and Lie Groups by S. Kumaresan. So these are the Indian edition available, which published from TRIM series of the Hindustan Book Agency. So that's it for today. I will give you a overview of the Lie group Lie algebra correspondence in the next class. So thank you very much for your attention. Thank you.